Have you ever looked up at the night sky and felt completely and utterly alone? I mean, really alone. Not just lonely, but cosmically insignificant. Well, I'm about to make you feel a whole lot smaller. Because what we're talking about today doesn't just make you feel tiny, it makes our entire planet, our sun, every star you can see with your naked eye feel like a single grain of sand on an infinite beach. We are going on a journey tonight, a journey to the edge of reality itself, a place where time stands still, where space is torn apart, where the very laws of physics as we know them simply cease to exist. This is a place so violent, so strange, so terrifying that for a century, even the great Albert Einstein himself doubted it could be real. But it is real. It's out there, right now, and it holds the key to everything. This is the full story of black holes. To understand the black hole, we have to go back, way back, not just a few hundred years, but to the very beginning of our universe. And we have to start with a simple idea, an idea so simple a child can understand it. It's called escape velocity. You know how it works. When you throw a ball up in the air, what happens? It always comes back down, every single time. That's Earth's gravity pulling on it. Now, if you want that ball to escape Earth's gravity completely, to fly off into space and never come back, you need to throw it really, really fast. For Earth, that magic number is about 25,000 miles per hour. Scientists call this the escape velocity. Now, let's do a thought experiment, a crazy one. Imagine you could take the entire Earth, everything, the mountains, the oceans, the cities, every living thing, and squeeze it down, crush it, compress it into a ball the size of a peanut. Just think about that for a moment. The entire mass of our world in something you could hold in your hand. The gravity on the surface of that tiny, impossibly dense peanut would be unimaginable. The escape velocity would be enormous. In fact, it would be faster than the speed of light. And here's the kicker, the most important thing you will hear in this entire video. Nothing, absolutely nothing, can go faster than light. It's the universe's ultimate speed limit. So, if the escape velocity is faster than light, then nothing, not a spaceship, not an atom, not even a single particle of light itself, could ever escape. The object would be completely and utterly dark, a hole in the fabric of space itself. Now here's something that might surprise you. This idea, this concept of a dark star, it isn't new. It's actually over 200 years old. Back in 1783, there was a man named John Michell. He was an English clergyman, a country parson, but he was also a brilliant natural philosopher. And he was sitting there thinking about gravity using Sir Isaac Newton's laws when he had a profound realization. He thought if light is made up of tiny particles, as Newton believed, then gravity should affect them too. So, if a star was massive enough, far, far more massive than our sun, its gravity would be so intense that it would pull those light particles back down to its surface. The star would be unable to shine out into space. He called them dark stars. It was a remarkable prediction made over a century before Einstein was even born. But here's the thing, Michel's dark stars were just a curiosity, a hypothetical oddity based on Newton's idea of gravity as a simple force. They weren't the monsters we know today. The real story,
The true horror couldn't begin until that entire idea of gravity was completely and utterly overthrown. Enter Albert Einstein. The year is 1915. The world is tearing itself apart in the First World War, but Einstein is at war with our very understanding of the universe. Then he unveils his masterpiece, his crowning achievement, the general theory of relativity. And let me tell you, this wasn't just a new theory, this was a new way of thinking about reality itself. Einstein didn't see gravity as a mysterious force pulling things across empty space. No, he saw gravity as geometry. It's the shape of the universe.
I want you to imagine something. Imagine the universe, not as empty space, but as a vast, four-dimensional fabric. Physicists call it space-time because Einstein showed that space and time are not separate things. They are woven together into a single, flexible cosmic sheet. Now, take that rubber sheet and stretch it tight. Make it smooth and flat. That's empty space-time, nothing in it. Now, place a heavy bowling ball right in the middle of it. What happens? The ball sinks down. It creates a curve, a dip, a valley in the fabric. That curvature, that dent in the universe, is what we experience as gravity. This was the revolution. The planets don't orbit the sun because of some invisible rope pulling on them. They orbit because they are rolling around the curve that the sun makes in space-time, like a marble rolling around inside a bowl. The sun creates a valley, and the planets are trapped, circling the slopes forever. Einstein published his theory, and it was a sensation. But it was also incredibly complex. The equations were so difficult that only a handful of people in the entire world could truly understand them. One of those people was a German physicist named Karl Schwarzschild. And here's where the story gets almost unbelievable. Schwarzschild was not sitting in a comfortable university office when he made his discovery. He was serving as an artillery officer on the brutal front lines of World War I, in the midst of the mud and the blood and the constant chaos of war. Between calculating shell trajectories and dodging bullets, he found the time to read Einstein's paper. And he did something extraordinary. He sat down in a war zone and he solved Einstein's equations. He found a mathematical description of what space-time would look like around a single massive point. He sent his solution to Einstein, who was absolutely astonished. Schwarzschild had found something truly bizarre. He found that if you crushed enough mass into a small enough sphere, the curvature of space-time would become so severe that it would literally pinch itself off from the rest of the universe. It would create a bottomless pit. At the very center, the mass would be crushed into a single point of infinite density, a place physicists call a singularity. And around that singularity, there would be a spherical boundary, a point of no return. Once you crossed that line, space-time itself would be flowing inward so fast that not even light could swim against the current. It was an event horizon, a horizon beyond which no events could ever be seen. For decades, these Schwarzschild singularities were considered a mathematical oddity, a bizarre and unphysical consequence of Einstein's beautiful equations. Even Einstein himself thought they couldn't possibly exist in the real universe. He believed that nature would find a way to prevent something so extreme. And for a while, it seemed like he was right. The universe appeared to be a calm and orderly place.
But in the 1930s, a brilliant young man from India was on a ship to England to begin his studies. His name was Subramanian Chandrasekhar. Everyone called him Chandra. And on that long voyage, he started to think about what happens when stars die. He was about to pick at a thread that would unravel the entire tapestry of our understanding. Chandra was studying white dwarfs. These are the final state of stars like our sun. When a star like the sun runs out of fuel, it can't fight against gravity anymore. It collapses down into an incredibly dense object about the size of Earth. A teaspoon of its material would weigh tons. It's held up against further collapse by a strange quantum mechanical pressure, the pressure of electrons being squeezed together, refusing to occupy the same space. But Chandra started doing the math. He calculated that this electron pressure has a limit. If a white dwarf is too massive, gravity will simply overwhelm it. He found the precise number: 1.4 times the mass of our sun. If a dying star is more than this mass, the Chandra limit, the white dwarf will collapse further. It will crush the electrons into the protons, turning them into neutrons. The star becomes a city-sized sphere of pure nuclear matter, so dense that a single teaspoon would weigh 1 billion tons. This is a neutron star. Chandra presented his work at a meeting of the Royal Astronomical Society in London in 1935. He was young, he was shy, he was brilliant. But the most famous astronomer of the day, a man named Sir Arthur Eddington, stood up in front of everyone and publicly ridiculed him. Eddington called Chandra's ideas stellar buffoonery. He said there should be a law of nature to prevent a star from behaving in this absurd way. Chandra was humiliated. His career was nearly destroyed. But here's the thing. He was right, and Eddington, for all his genius, was wrong. It was a painful reminder that science isn't always objective. It's done by humans with egos and biases.
But the idea didn't die. In 1939, a physicist named J. Robert Oppenheimer, the same man who would later lead the Manhattan Project to build the atomic bomb, took Chandra's idea to its terrifying conclusion. He and his student showed that if a star is massive enough, several times the mass of the sun, even the neutron star wouldn't be able to hold. Gravity would have no rival. There is no force in the universe that can stop it. The star would undergo a catastrophic, relentless collapse, crushing itself down into an infinitely small, infinitely dense point, a singularity, and around it an event horizon would form. The black hole had become an inescapable, inevitable prediction of physics. Oppenheimer had described the birth of a monster. For the next 30 years, black holes remained a ghost story. They were a terrifying prediction, but no one had ever seen one. How could you? They're black. They don't emit light. They were invisible. Physicists were like detectives looking for a monster in the dark with no proof it even existed. Then, in the 1960s, a technological revolution happened. We launched rockets into space, carrying telescopes above Earth's blurring atmosphere. We started seeing the universe in a whole new light, including X-rays, which are blocked by our atmosphere. And what we found was shocking. We found incredibly powerful sources of X-rays in distant galaxies, which we called quasars. These quasars were so bright they outshone entire galaxies of 100 billion stars, yet they were coming from a region no bigger than our solar system. It was like finding a single, impossibly bright light bulb in the middle of a vast, dark city.
The only thing in the known universe that could generate that much power from such a small region was gas, superheated to millions of degrees, swirling and screaming as it fell into an object of unimaginable gravity, a supermassive black hole. A black hole millions or billions of times heavier than our sun, lurking at the heart of a distant galaxy. And then, closer to home, in our own Milky Way galaxy, we found a system called Cygnus X1. It was a powerful source of X-rays. Astronomers pointed their telescopes at it and saw a bright blue supergiant star. But something was wrong. This star was wobbling. It was locked in a gravitational dance with something invisible. By measuring its wobble, they could calculate the mass of its invisible partner, and the number was staggering. The invisible object was at least 10 times more massive than our sun. There was no other option left. The only possibility was a black hole. Material from the blue supergiant was being ripped away by its invisible companion, forming a swirling disk of superheated gas, an accretion disk that was hot enough to blast X-rays into space just before the gas vanished behind the event horizon forever. Cygnus X1 was the first strong candidate. The monster wasn't just a theory anymore. It was real. It was here, in our own cosmic backyard. So now, let's do something no human will ever do, at least not for thousands of generations. Let's get up close and personal. Let's imagine you're the bravest astronaut in history, and you have a one-way ticket to a black hole.
What would you see? What would you feel? First, you'd need to pick a black hole. Let's choose a quiet one, a stellar mass black hole with no swirling disk of gas to fry you. As your ship gets closer, the view out your window becomes strange. The gravity of the black hole is so strong, it's bending the light from the stars behind it. The entire sky begins to warp and distort, smearing into a brilliant ring of light around a perfect sphere of perfect darkness. That sphere is the shadow of the black hole, the event horizon silhouetted against the light of the universe. You're approaching the point of no return. You might think you could just fly up to the edge, take a look, and then fire your engines to come home. But that's impossible. In Einstein's universe, space and time are one, and as you approach the event horizon, something terrifying happens to time itself. To an outside observer, your friends watching from a safe distance in their own spaceship, you would appear to slow down. Your movements would become languid, then frozen. The light from your ship would become redder and redder, shifting out of the visible spectrum into infrared, then radio, until you simply faded from view, forever frozen on the edge of the black hole. You would be gone, but your ghostly image would be stuck there for the rest of the universe's life. Pause. Then voice becomes calm, almost peaceful. But for you, in your ship, nothing would feel strange at first. You'd cross the event horizon without even noticing it. It's not a wall, it's just a point in space. But then, you'd realize you can't get out. It's not that you're being held back by a force, it's that the paths out of the hole lead only inward. Space-time itself is flowing into the singularity, faster than light. All possible paths, every direction you could possibly point your ship, leads only one way, down. The singularity is no longer a place in front of you, it's a moment in your future. It's as inevitable as tomorrow morning. And as you fall, the tidal forces become insane. The gravity at your feet is massively stronger than the gravity at your head. You are being stretched. Physicists call this spaghettification, a term coined by the great Stephen Hawking.
You are pulled into a long, thin strand of atoms, then ripped apart. Your body, your ship, every atom that makes you who you are is torn apart into a stream of elementary particles, all plunging toward the singularity. In the final moment, all that you were, all the information that composed your existence is crushed into that single, infinitely dense point. You have become part of the singularity. Your story ends. This brings us to the man who became the face of black hole research, the man who spent his life trapped in a failing body, but whose mind roamed free across the cosmos. Stephen Hawking. For most of the 20th century, physicists thought black holes were eternal. They were cosmic sinkholes. Whatever fell in was gone forever, erased from our universe. But in 1974, Hawking dropped a bombshell. By combining the two great theories of physics, general relativity, the world of the very big, and quantum mechanics, the world of the very small, he made a stunning discovery.
Black holes aren't black. They glow. They emit radiation. It's now called Hawking radiation. Now, this idea is mind-bending, so stick with me. Quantum mechanics tells us that empty space isn't really empty. It's a frothing, seething foam of energy. Pairs of particles and their antiparticle counterparts are constantly popping into existence for a brief instant before annihilating each other and disappearing back into nothingness. It happens everywhere, all the time. But right at the edge of a black hole's event horizon, something different can happen. The gravitational pull is so strong, it can tear the pair apart before they annihilate. One particle falls into the black hole, while its partner escapes into space. To an outside observer, it looks like the black hole is emitting a particle. It's glowing. Now here's the profound part. Energy must be conserved. The energy that escaped had to get its energy from somewhere. It borrowed it from the black hole's gravitational field. This means the black hole just lost a tiny, tiny amount of its mass. Over time, over billions and trillions and quadrillions of years, this process continues. The black hole slowly evaporates, it shrinks, and as it gets smaller, it gets hotter, and the radiation gets faster and faster. In its final moments, the black hole would explode in a tremendous burst of energy, and then it's gone. The black hole has vanished. This leads to the most profound paradox in modern physics, the black hole information paradox. What happens to everything that fell in? If the black hole evaporates and disappears, what happens to the information that was carried by the objects that fell into it? Does it just vanish? In quantum mechanics, information can never be destroyed. You can burn a book, but the information in that book is not destroyed. It's just scrambled into the atoms of the smoke and ash. In theory, you could, with enough knowledge, reconstruct the book. But if a book falls into a black hole and the black hole evaporates, is the information about that book lost forever? Does it escape with the Hawking radiation? This is a battle between general relativity, which says information is lost, and quantum mechanics, which says it can't be. The resolution of this paradox will likely lead to a deeper understanding of reality itself. Today, we know that black holes are not just rare oddities, they are everywhere. We believe there are millions of stellar mass black holes scattered throughout our Milky Way, the silent graveyards of ancient, massive stars. And at the very heart of our galaxy, 26,000 light-years away, lies a true behemoth. It's called Sagittarius A star. It has the mass of 4 million suns, all crushed into a space smaller than our solar system.
For decades, we inferred its existence by watching stars whip around it at incredible speeds, like comets swinging around our sun. One star, called S2, orbits this invisible giant once every 16 years, coming within 17 light hours of it. Its orbit is a perfect, elegant dance that can only be explained by the presence of an object with 4 million solar masses that emits no light. It is a supermassive black hole, and it's our black hole. And recently, we've done the impossible. We've taken a picture of one. In 2019, the Event Horizon Telescope, a planet-sized array of radio observatories stretching from Hawaii to Spain to the South Pole, revealed the first ever image of a black hole. It was the supermassive black hole in the center of a galaxy called M87, 55 million light-years away. The image wasn't a photograph, it was a reconstruction of years of data. And it showed exactly what theory predicted: a bright, lopsided ring of orange light surrounding a perfectly dark circular shadow. That shadow is the event horizon. That is the point of no return. We were looking at the edge of infinity. In 2022, they released the image of our own galaxy's black hole, Sagittarius A star. It was harder to capture because it's smaller and more variable, but there it was, the monster in our own backyard, silent, patient, waiting. But the story of black holes is not just one of destruction. It is, in a beautiful and profound way, a story of creation. Think about your own body, the iron in your blood, the calcium in your bones, the oxygen you breathe. These elements were not created in the Big Bang. They were forged in the hearts of massive stars. And those elements were only scattered across the galaxy when those stars died in colossal supernova explosions. And what triggers the supernova of the most massive stars? The birth of a black hole at their core. The birth of a black hole is the most powerful explosion in the universe since the Big Bang itself, and it seeds the cosmos with the building blocks of life. Black holes are the great recyclers. They destroy, and in their destruction, they create. The supermassive black holes at the centers of galaxies seem to play a crucial role in how their host galaxies grow and evolve. They can heat up gas and prevent too many stars from forming, regulating the galaxy's growth in a cosmic feedback loop. A galaxy and its central black hole are not separate entities. They are a single, co-evolving system, locked in a gravitational and energetic dance for billions of years. So where does that leave us? We are a species of conscious stardust, living on a small blue planet in the quiet suburbs of the Milky Way, safe in the stable gravity of our sun. And yet, we have the audacity, the sheer intellectual courage to reach out across the cosmos and grapple with the most extreme objects in existence. Black holes represent the ultimate limit. They are the place where our current understanding of physics breaks down. They are the border between the known and the unknown. They force us to ask the biggest questions. What is space? What is time? What is the true nature of reality? From a dark star in the mind of an 18th century clergyman, to a terrifying solution on a World War I battlefield, to a paradox that challenges the very foundations of science, the black hole has become the most profound and humbling object in the universe. It is a monster. It is a mystery. And in its perfect silent darkness, we are given a gift, a mirror. In the shadow of the black hole, we can finally see the faint, brilliant outline of our own existence. We are the universe, conscious and curious, looking back at itself and wondering what else lies out there in the great, cosmic, dark.